Quasi-hereditary algebras, lecture 20, problem session. Problem 1. Let K be an algebraically closed field. Let A be the K algebra given by the following quiver and relations. We have two vertices, 1 and 2, and two arrows, alpha from 1 to 2 and beta from 2 to 1. And the relation is that alpha after beta is 0. Consider the algebra B given as a tensor product of A with the algebra of dual numbers. Recall that the algebra of dual numbers is a quotient of the polynomial algebra k of x modulo the ideal generated by x squared. Show that the algebra B is properly stratified with respect to the order 1 smaller than 2 and compute its linear dual. Solution. We start by writing down the diagrams of the indecomposable projective B modules. So here are these diagrams. The indecomposable projective B module P1 has a basis given by all passes which start at 1. So we have the trivial pass from 1 to 1, that's the top element of this module, and then starting from this 1, we can go by x to 1 or by alpha to 2, and then from 2 we can continue by beta to 1, or we can go by x to 2, and here we have a connection between 1 and 2 given by alpha, and this commutes because alpha and x commute. And finally here, from this 1 we can go by x to this 1, and we can also come to this one by beta from this 2. And again beta and x commute by definition. So this is a diagram of P1. Here is P2, we start at 2, we go by beta to 1 or by x to 2, and from 1 we can go to the lower one by x or by beta from this 2, and again beta and x commute. So these are our diagrams of the indecomposable projective modules, and we can immediately read off the diagrams of the standard B modules. So delta 2, the second standard module is just the projective module. So we have 2 on top, 1 and 2 in the middle, and 1 in the circle. And delta 1 is a quotient of P1 by the trace of P2. So here we see a copy of P2 in P1. When we factor this copy out, what remains is 1 on top and 1 in the circle. This is our delta 1. And now it is very easy to see that our projective modules have standard filtrations. So P2 is a standard module, so there is nothing to see here. And as we just said, in order to obtain delta 1, we took P1. There was a copy of P2 inside P1 and we factored it out. This gives us a standard filtration of P1. So this implies that B is a strongly standardly stratified algebra with respect to our order where 1 is smaller than 2. Also let us note that swapping alpha and beta and fixing x gives rise to an isomorphism between the algebra B and B opposite. And this isomorphism of course keeps the primitive idempotence at 1 and 2. So this means that the category of all B modules has a simple preserving duality, and so since it's strongly standardly stratified, it follows that B is a properly stratified algebra. So now we need to compute the Ringel dual of B. For this we need the tilting modules, and for this we need the proper costandard modules. So here are the indecomposable injective B modules. So P1 is the indecomposable injective module I1, and I2, this should be I2, has circle 2, and then to this 2 we can come from 2 or 1, and the top of it is 1. So it's just the dual of the indecomposable projective module P2. So this is a P2 dual, this is P1 dual. And now we can see the costandard modules. So I2 is costandard, it's a nabla 2. And here we have a homomorphism from I1 to I2, which is surjective. So we see here a copy of I2 in the top, and the kernel of this homomorphism is nabla 1, which as we see is isomorphic to delta 1. So these are our costandard B modules, and now here we can see the proper costandard B modules. Nabla 1 overlined is simple, and nabla 2 overlined is just 1 on top of 2. So here is our nabla 2 overlined, and here is our nabla 1 overlined. So now let us discuss tilting b-modules. The module P1, as we already observed, is injective, and so it must be a tilting module. And of course, since P1 contains L2 somewhere, the only possibility for it to be is the tilting module T2. Also note that the standard module delta 1 is automatically tilting because nabla 1 overlined is simple, and so it filters delta 1, and so delta 1 is isomorphic to T1. So our tilting modules T1, it is the same as delta 1 or as nabla 1, and T2 is the same as P1 and is the same as I1. So these are our indecomposable tilting modules. Now we need to compute the Ringel dual of B. So let us first note that T2 is P1. So we already have one indecomposable projective module as tilting. And also T1 is a submodule of P2. If we look at our P2, here is our P2, the module T1, which is 1 on top of 1, is a submodule of P2. Okay, great, so T1 embeds into P2. Moreover, it coincides with the trace of P1 and P2. It contains all ones and is generated by these ones inside P2. And of course, trivially, T2, which is P1, is the trace of P1 and P1. And so our tilting modules coincide with the trace of T1 in the indecomposable projective modules. Therefore, any endomorphism of P1 plus P2 can be restricted to this trace. We can always restrict endomorphism to traces. And so an endomorphism of P1 plus P2 restricts to the trace of P1 in this module, and this trace is T2 plus T1. Also, let us note that the socle of both P1 and P2 is L1. So if you look at our pictures of projective modules, both of them have 1 in the socle, and that's it. So, which means that the socle belongs to our trace, and this implies that our restriction maps non-zero homomorphisms to non-zero homomorphism. A homomorphism is non-zero if and only if its image is non-zero, but then the image must contain something in the socle, and if the socle is simple and intersects the trace, so this means that our image will belong to the trace. So the restriction of a non-zero homomorphism is non-zero. And this implies, of course, that we have the restriction algebra homomorphism from B to R of B, which sends non-zero elements to non-zero elements. So B is a subalgebra of R of B. And we actually claim that B is equal to R of B. So the subalgebra B inside R of B is actually the whole R of B. And to prove this, it remains to show that they have the same dimension. And for this, it is enough to show that the Cartan matrices of these two algebras coincide. So let us compare the entries of the Cartan matrices. P1 is T2. So homes from P1 to P1 are the same as homes from T2 to T2, and the dimension is 4. So now P1 is T2, so home from P1 to P2 is the multiplicity of L1 and P2, which is 2, and home from P1 to T1 is the multiplicity of L1 and T1, which is also 2. So here we have 2. So here we have to compute a little bit. Home from P2 to P1 is the same as from T1 to T2, is two-dimensional. Let's look at the pictures. So home from P2 to P1 has dimension the multiplicity of L2 in P1. This is 2. And home from T1 to P1, so we take this 1, 1, and we map it into P1. We can map 1 here. We have an embedding, and we have a map which maps top to the socle. So it's also two-dimensional. And the endomorphism of P2 is two-dimensional. The endomorphism of T1 is also two-dimensional. This means that all entries of the Cartan matrices are the same and completes the solution to problem 1. So indeed, in this case, the Ringel dual is isomorphic to the original algebra. Problem 2. Let K be an algebraically closed field. Consider the path algebra of the following quiver. We have vertices which are given by positive integers 1, 2, 3, 4, and so on. For each vertex I, we have an arrow alpha I from I to I plus 1. And for each vertex I, we have an arrow beta I from I plus 1 to I. And we have the following relations. Alpha I plus 1 after alpha I is 0 for all I. Beta I after beta I plus 1 is 0 for all I. And beta I plus 1 after alpha I plus 1 is equal to alpha I after beta I for all I. Show that this algebra is quasi-hereditary with respect to the natural order and compute its renal dual. Solution. So let us start by drawing the pictures of projective modules. So here almost all modules look the same, apart from the projective P1. So 1 is the starting point of our picture. So from 1 we can only go to 2 by alpha 1 and then come back to 1 by beta 1, and then we cannot do anything. And for any I greater than or equal to 2, Pi looks as follows. From I we can go by alpha I to I plus 1, or by beta I minus 1 to I minus 1, and then we can come back to I using alpha I minus 1 or beta I respectively, and this diagram commutes. So this allows us to compute the standard modules. So if we take the traces of everything bigger, so for the case of P1 we just get the simple L1 because we have to kill this 2. And in the case of Pi, where I is greater than or equal to 2, we get I on top of I minus 1, because we need to kill this I plus 1, and so we kill this I. So these are our standard modules, and we readily see that our projectives have standard filtrations. So P1 has delta 2 as a submodule, and the quotient is delta 1. And if I is greater than or equal to 2, Pi has delta I plus 1 as a submodule, and the quotient is Pi. And so our algebra is quasi-hereditary. Also, it has a simple preserving duality, which is given by swapping alpha I and beta I for all I. And it is very easy to see that all projective modules are self-dual, so in particular they are injective. So all projectives for this algebra are injectives, and so they must be tilting. So in fact, Pi is equal to the tilting module T I plus 1 for each I. And so we have only one tilting module left, which is T1, and this is always L1 because 1 is a minimal element. Hence, our tilting modules are as follows. So T1 is just the simple L1, T2 is P1, T3 is P2, and so on. Now, if we want to compute the Ringel dual, we need to compute the endomorphism category of the indecomposable tilting modules. This has as a pool subcategory the endomorphism category of projectives over our algebra, and this of course gives us our original quiver back. And of course we need to recall that for the Ringel dual we take the opposite order on simples. Now we have one additional tilting module, which is T1, and we will represent it by 0 in our quiver for the Ringel dual, and it is only involved in the following non-zero homomorphisms. So we can map T1 into T2, we embed T1 into T2 here, or we can project T2 onto T1. We cannot do anything else. So we have the homomorphism alpha 0 from T1 to T2, and the homomorphism beta 0 from T2 to T1. And for these, we have the same relations as for the original quiver, but now including the new arrows, and the additional relations that beta 0 after alpha 0 is 0. Indeed, if you start from here, we embed it into T2, and when we project back, the socle is killed. This gives us the relation beta 0 after alpha 0 is 0. This implies that we have the following quiver. We have vertices starting from infinity and then going to 4, 3, 2, 1, 0. And then the arrows beta I from I minus 1 to I, arrows alpha I from I to I plus 1, and the relations, now the same as in the original quiver, 2 alphas give 0, 2 betas, 2 consecutive betas give 0, and then we have the starting from any I, doing beta I and then alpha I is the same as doing alpha I plus 1 and then beta I plus 1. And finally, we have the additional relations that beta 0 after alpha 0 is 0. That's a description of our Ringel dual via quiver and relation. So this completes problem 2. Problem 3. Prove that the temporally Lieb algebra TL sub n q, k is cellular over any algebraically closed field K and for any value of the parameter Q. Let us remind that the temporally Lieb algebra TL sub n q, k has a basis consisting of all planar diagrams up to isotopy in which two endpoints are connected in pairs, and these are sometimes called temporally Lieb diagrams, and we will see some examples on the next slide. The multiplication in this algebra is given by concatenation of the diagrams, followed by a certain straightening procedure, which will be explained on the next slides, and the parameter q appears in the straightening procedure as a coefficient. Since we have a basis of the temporally Lieb algebra given by non-crossing connections of two endpoints, the dimension of this algebra is the nth Catalan number. So here are the examples. There is only one temporally Lieb diagram for n is equal to 1, so we have 2 points and they are connected. For n is equal to 2, we have two diagrams, so in each diagram we have 2 points on the left, 2 points on the right, and then they are connected. They are connected either directly, so left points connected with right points, or they are connected in pairs. 2 points on the left are connected and 2 points on the right are connected. We have two diagrams. Here are the 5 temporally Lieb diagrams for n is equal to 3, so here they are. Again, each diagram has 3 points on the left, 3 points on the right, and then they are connected. So either they are connected from left to right on the first diagram, or the top one is connected from left to right, and then two others are connected on the sides. Or we connect the top left point with the bottom right point, and we connect the others on the side. Or the bottom left with top right, the others on the side. Or in the bottom it's connected from left to right, and the 2 points are connected on the side. So we have 5 temporally Lieb diagrams for n is equal to 3. Here is an example of multiplication. So here is one temporally Lieb diagram, here is another temporally Lieb diagram. So in the first one we take the right points and we identify them or connect through with the left points of the second diagram, and then we read the diagrams through. When we read the diagrams through, we get a diagram, and then in the middle here we might get some connected components which do not contribute to the new diagram. So these components are removed, and each component which we remove contributes with the coefficient q. So here we remove only one component, this component, so our coefficient is q to the power 1. If we would have removed 2 components in the middle, the coefficient would be q to the power 2, and so on. So the appearance of this parameter, q to some power, corresponds to the removal of a number of connected components here in the middle during our straightening procedure. Okay. Let us first note that there is an obvious anti-involution on the temporally Lieb algebra, which is given by flipping the diagram around the vertical axis. Here is an example. If you have a temporally Lieb diagram for TL3, so here the top left point is connected to the bottom right point, and then the rest is connected automatically. If we flip it, we will get that the bottom left point is connected to the top right point, and the rest is connected automatically. So this is how our involution works. A definition: given a temporally Lieb diagram, a propagating line in this diagram is a connection between the left and the right point of this diagram. And the number of propagating lines of some diagram is called the rank, and denoted rank of alpha, so where alpha is a diagram. So for example, if we take as alpha the diagram from TL3 where all points are connected from left to right, the rank will be 3. And if we take the diagram where the top point is connected from left to right and the bottom points are connected on the side, the rank will be 1. This is the only propagating line. And here we have 3 propagating lines. Okay? Let us note that n minus rank of a diagram is always an even, non-negative integer. That's because when we have propagating lines, we take them away. The rest of the points should be connected in pairs on both sides. Okay, so now if k is a non-negative integer which is less than or equal to n, of the same parity as n, let us denote by I sub k the linear span in the temporally Lieb algebra of all diagrams of rank at most k. And also we denote by j sub k the linear span of all diagrams of rank exactly k. And then of course we have that I sub k is equal to j sub k direct sum plus j sub k minus 2 direct sum and so on. That's by definition. Moreover, it is easy to see that each I sub k is an ideal. That's because if we multiply two diagrams alpha and beta, the rank of the outcome will be less than or equal to the minimum of the ranks of alpha and beta. In other words, we have a chain of ideals, the chain of two-sided ideals. Ideal In contains the ideal In minus 2, this contains the ideal In minus 4, and so on. We have a decreasing chain of ideals in our temporally Lieb algebra. So to prove that temporally Lieb algebra is cellular, we need to prove that each subquotient in this chain is a cell ideal in the quotient of the temporally Lieb algebra by the smallest of these two ideals. Okay, let's prove that. Let us denote by delta n comma k the linear span of all temporally Lieb diagrams alpha in the temporally Lieb algebra, which have rank k and such that the propagating lines are connected to the top k bullets on the right. So here is an example. The space delta 3, 1 has two elements. The diagram where the first points are connected and the diagram where the bottom point on the left is connected to the top point on the right. From the definition, it is easy to see that the quotient of our delta n comma k modulo I sub k minus 2 is a left ideal inside I sub k modulo I sub k minus 2. Here is a hint. Left multiplication cannot change the connections on the right. So if you multiply this diagram on the left, this connection is automatic. Of course, it is possible that we can add some connections on the right, but then this will decrease the rank and end up in I sub k minus 2, and so it will be 0. And then there is no problem. For two diagrams alpha and beta, let us denote by alpha diamond beta their product, but with one small correction. When we remove the connected components, we just ignore them. There is no parameter appearing. So alpha diamond beta is just the diagram, the underlying diagram of the product. So we do not write any powers of Q. Then, if we take alpha tensor I of alpha and map it to alpha diamond I of alpha, this gives rise to an isomorphism between the tensor product of our left ideal, tensor over k, its image under our involution iota, and the ideal ik modulo ik minus 2, and this is an isomorphism of bimodules over our quotient of the temporally Lieb algebra. From the geometric nature of our involution and from the definition of the product, it is very easy to see that iota applied to alpha diamond beta is equal to iota of beta diamond iota of alpha. And this implies directly from the definition that ik modulo ik minus 2 is a cell ideal of the temporally Lieb algebra modulo ik minus 2. And so all conditions of the theorem by Koenig and Xi are satisfied, and this implies that TLNQK is a cellular algebra. It is very interesting to observe that this algebra is not quasi-hereditary in the case when n is even and q is 0. So we have a genuine example of a cellular algebra here, which is not quasi-hereditary, but in most cases, for most values of the parameter, it is. Here are some extra problems and questions, mostly related to the last problem which we discussed. Prove with all details that the temporally Lieb algebra is not quasi-hereditary if n is even and q is 0. Second problem question, prove with all details that iota of alpha diamond beta is equal to iota of beta diamond iota of alpha. Problem question 3, prove with all details that delta n comma k modulo I k minus 2 is a left ideal inside I k modulo I k minus 2. Problem question 4, explain why n minus rank of alpha is always even for any temporally Lieb diagram alpha. And problem question 5, prove with all details that for any two temporally Lieb diagrams alpha and beta of the same size, the rank of alpha composition with beta is less than or equal to the minimum of the rank of alpha and the rank of beta. So this finishes the course. Thank you very much for this course and for listening.